nice.
Okay, sorry about the hitch. Okay, so this talk is clearly related to the previous one by Giuseppe and Eve, but as you'll see, heads off in a somewhat different direction. I've made this talk quite non-technical, so hopefully it'll be even understandable to somebody that doesn't know about the situation calculus. So details will be in the paper or in the poster session. So by way of motivation, in reasonable action, agents, well, they have knowledge about the world, they carry out actions, they do sensing, but pretty clearly in practice, none of this works as intended. Beliefs can be incomplete, inaccurate, or incorrect. Actions may fail, they may have unexpected consequences, and generally actions may be non-deterministic. Flipping a coin is the standard example. And sensors may behave similarly. They may report incorrect results or do something curious. Okay, so our goal here is to develop a general model, a qualitative model of an agent that can reason and maintain its beliefs, and the emphasis here will be on beliefs in such cases. So what we do is develop an extension to the situation calculus that allows for the agent to hold contingent beliefs, so it believes that something holds, and counterfactual beliefs. These things are implausible. They could be the case, but I don't think they actually hold. And I've got it in scare quotes, non-deterministic actions. Okay, so here's a scenario we'd like to deal with. An agent flips a coin. It now believes that the coin shows heads or tails. It takes a look at the coin and learns it shows heads. And we want to allow for the possibilities. Maybe the sensor was erroneous and gave us the wrong report. And maybe in a really weird situation, the coin landed on its edge. Okay, situation calculus, a 10-second introduction. It's a first order theory for reasoning about actions. Actions take a state of the world from one state to another. States of the world are called situations. They're not really states of the world, but close enough. So here an agent in this example is holding object A in situation S0, and it's not holding it after it drops the object. Our modeling of belief is as in essentially possible world semantics, but encoded in first order logic. Here's the account due to Searle and Levesque. And if we take a look at the diagram, in the first oval, there's a set of situations modeling the agent's beliefs. It executes action A1 to come up with a new set of situations. In those situations, on the left-hand side, you can see that phi is believed. On the right-hand side are those situations where not phi is believed. It does a sensing action, learns that phi is the case, and so it only those phi situations are accessible. So we're working with this, but generalizing this approach. So, as I said, the approach elaborates on the previous scheme, and what we do is we add plausibilities to situations. So the most plausible situations characterize the agent's beliefs, where lower plausibility, lower numbers are more plausible. We allow actions with non-deterministic outcomes, and action outcomes can also have different plausibilities. It's a whole lot more likely that if a coin flip is going to land on its head than it is on its edge. So we use a three-place fluent, B, for modeling those situations the agents considered possible along with an attached plausibility. So B, S prime NS, where n is greater than or equal to 0, says in situation S, the agent considers S prime to have plausibility N. And again, beliefs at S are characterized by those situations with minimum plausibility. Non-determinism. Well, I put it in scare quotes because our stance is the world actually is deterministic. Every state of the world is uniquely determined by its predecessor state and the action executed. Where does non-determinism come in? Well, it's an epistemic notion. It reflects an agent's limited knowledge and perception. Consider a coin flip. If an agent had very, very fine-tuned motor control, it could do a flip heads or a flip tails action. It doesn't have this, and so it doesn't have the control to end up with a heads or a tails. Other examples, inadvertently pressing the wrong light switch. You've got a bank of switches, you aim to push one, you push one a little ways away. And maybe just actions failed for no known reason. You do a pickup action and you take a look at the result and something went wrong and it failed. Okay, so the key point is we address these unpredictable outcomes by assuming that there's action arguments that are beyond an agent's control. So what this means then is for us, an actions arguments fall into two groups. We've got two sets of arguments. First of all, those that are controlled by the agent. This is what you see all the time in the situation calculus. So in a move action, the agent will decide where it intends to move to. And there's going to be those arguments that are controlled by, we'll call it nature. And these are beyond the agent's immediate control. It has no say regarding these arguments. So for example, in moving, a move action might be off by n units where larger n are less plausible. So n equals 0 is most plausible, 1 is a lot less plausible, and so on. Okay, so to implement this, we add two predicates to the theory. APL stands for action plausibility, has an action argument, plausibility, situation, and what it does is it gives the plausibilities for those arguments that nature can control. So let's take a look at flipping a coin. Flip has two arguments. X is the coin that the agent elects to flip. Y is an outcome determined by nature. And in flipping a coin X, Y has the following values. Well, it's heads or it's tails with plausibility 0. Something goes wrong and it just simply fails, has plausibility 1. And very implausible, it lands on its edge. It's possible these arguments could be related, even though the agent has no control over Y. We might want to elaborate this example and talk about an unfair coin being flipped. Second, we have a predicate IEQ, and that just says that two actions are intentionally equivalent. Basically, the agent can't tell the difference between them. Same action name and same parameter action argument, values set by the agent. Okay, so an agent's beliefs evolve according to action instances and their associated plausibilities. So if an agent flips a coin, it will believe, that is, the plausibility will be 0, the coin shows heads or tails. It allows for the possibility that the flip action failed or that the coin landed on its edge. Okay, sensing, it's an analogous approach. We use guarded action fluence, basically close to the approach by DiGiacomo and Levesque with plausibilities. So we can say a light sensor usually works, but may give an off, on, or parity error. So if the agent is at location X, and this is the argument controlled by nature, things are fine, then sensing works as you would expect. If nature decides there's a parity error, then the result is the opposite of the actual state of the light. If there's a transitory off failure, the result is off, similarly on, okay? And here we have the plausibility values. Most plausibly, the sensor works. And here we've decided that other things have plausibility 1, that implausibly something's gonna go wrong. Okay, so the B Fluent evolves according to actions executed. So again, we have, this encodes that at situation S, S prime has plausibility N, and we characterize B using a regular successor state axiom. Everything here is just an elaboration of Reiter's basic action theories. So in the case that we've got B S prime N of S holding for some, whoops, sorry, that's a typo. I shouldn't have that N prime there. We would have this successor here, right? The agent does action A, and so do A prime S prime with plausibility. N prime is going to hold just if, well, A prime is an alternative action to what was actually executed, And this plausibility here depends on the action here and the original plausibility in here. So we call this extensional belief, and it's the standard notion of belief in the Shirl-Levesque approach. Okay, so here's an example, toggling a light switch. So toggle usually works. We assume it works. Implausibly, it might fail. Sensing, we assume, is correct. Sensing cannot fail in this axiomatization, in this example. The agent knows for a fact that the light is on. It executes two toggles. It turns out the first one fails, but the agent wouldn't know this immediately because that's controlled by nature. And then it senses the state of the light. And so here is a diagram. A stack of dots indicates an agent's epistemic state. And as we move to the right, that indicates the evolution of the agent's beliefs. So at the outset, it believes that the light is on. It executes a toggle. It believes that the toggle worked. And in the darker line here, this is what's actually happened. It failed. It executes another toggle. And so again, we have different outcomes resulting in, at this point, the agent believes that the light is on. It does a sensing action. Sensing is correct, and the light's not on, it's off. So we lose the situations where on holds, and the agent comes to believe that the light is off. And it also would believe one of the toggle actions fails, but it doesn't know which. Okay, we can elaborate on this and consider sensing. And on the next slide, I'm going to show you where sensing may also fail, but it's going to be more reliable than the toggle action. So here we say sensing usually works, but implausibly reports an on result. And this is the resulting state we get here, right? It was the same as before, except this allows very implausible situations where the light is on. If sensing failure had implausibility 1, then this particular situation would have plausibility 1. And at that point, where sensing and toggling fail with the same implausibility, the agent wouldn't know if perhaps sensing had also failed. I'll wrap up, so I won't wrap up. How am I doing for time? Not so well. I'm going to skip intentional belief. It's a distinct notion of belief. You can see about it in the paper, and just go to the conclusions. So we've developed a model of an agent that gives an account of contingent. The agent believes unreservedly the coin is heads or it's tails, but other possibilities too. Possibly it's on its edge, along with a notion of epistemic non-determinism. Non-determinism is a function of the agent's beliefs, not the external world. And it allows for actions with unexpected consequences and censors that may not behave correctly. We suggest the account is very general. We show in the paper that it subsumes the approach of Shapiro, Pagnucco, Levesque, and Lesperance. We developed 2 accounts of belief, extensional and intentional. Intentional, very briefly, is just beliefs evolving solely from the point of view of the agent with no access to the actual real world. So what would the agent believe if it gets a report that the light is on, for example? And we show how these 2 relate. There's a fair bit we're interested in doing for future work. Which is to say Jens, has been looking at regression and progression. We suggest that the approach is suitable for a basis for epistemic planning. This would be the intentional notion of belief. And I think it can also be suggest that it could be used for a more nuanced approach to approaches to belief revision. So that's what I have. If I have any time for questions, I'm happy to take them.